Finally, Sunshine has multiple activities and we can move between them using intents.
We also know how to use implicit intents to integrate activities from other apps. In this lesson, we'll dive into just how the Android framework deals with your activities, in particular how the activity lifecycle may be different from what you're used to from other platforms and environments.
Don't worry, there's plenty of code for you to write.
Yes, plenty of code. Lots and lots and lots of code.
We'll move Sunshine along, implementing an underlying database and wrapping that in a content provider. Everything you need to know to use persistent storage.
The goal is to ensure your app provides a seamless, efficient experience for your users, even when networks may be slow or unavailable. Okay, so before Dan gets carried away with databases, let's look at what happens when you use an intent to transition between activities. Within Sunshine, if you tap on a list in the main activity, it opens up the detail activity. But the main activity remains on the backstack, ready to reappear as soon as you hit back. Now in that example, both activities are within the same app. But as we learned in Lesson 3, you can also launch the browser or Maps app from Sunshine. Or for that matter, the user can hit home and launch apps from there, or they can use the recents key or switch to another app using notifications. All of these options mean you can end up with a lot of apps on your backstack. Now keep in mind that our resources on devices are extremely limited, so it's not a good idea to have dozens of apps sitting idle in the background. Android solves this for us, so you don't have to use those awful task killer apps. So how does it do that? Well, it kills low priority applications that you haven't used in a while. We'll go into detail on exactly how it figures out which app needs to die in Lesson 6, but for now, it's important to realize that your app isn't in control of its own destiny. It can be killed at any time. So you need to know how to deal with that, and that means understanding the life cycle of an activity and the signals we get from the framework to indicate its progress through the lifetime. A platform which terminates apps on its own is a pretty radical departure for anyone like me who cut their teeth on desktop WinForms development. If you come from a similar background, you probably have a pretty good idea of what to expect in terms of lifecycle event handlers. You start with the onCreate callback, where you build and wire up your UI. Once that's done, your activity has been created. It likely won't be a surprise to you that there are also event handlers for when the activity becomes visible, which is on start, and another for when it gains focus and becomes the active foreground app, which is on resume. That same sequence then happens in reverse. On pause indicates that the activity has lost focus, followed by on stop when the app is no longer visible. Finally, there's an on destroy method indicating the end of the app lifecycle. When your app is first launched, you'll quickly move through these states: create, start, resume, one after the other. But within the full application lifetime, from when onCreate is first called until the app is finally terminated, it will move through the active lifetime and the visible lifetime many times. Let's look at those in a little more detail. The active lifecycle is when your activity is in the foreground and has focus. Here it's actively receiving input from user events and no other activities are obscuring it. On pause is called and the active lifetime ends as soon as your activity is partially obscured, like in this example. You can see here the permissions dialog is displayed in front of Google Play for an app install. Or the same thing happens when you have another activity trying to fulfill an implicit intent and the user needs to make a selection. So to make efficient use of limited resources, you'll want to use these signals to adjust your app's resource burden. So most updates to your UI can be paused when this lifetime ends, which is announced by onPause. But as you see, the app is still visible, so you shouldn't pause any processes that are drawing your UI. The visible lifetime, on the other hand, continues whenever the app is at all visible and ends as soon as it's completely obscured by another app, like this. At this point, our app has moved to the background. So when you see onStop, you know the user can't see your app at all. So while onCreate and onDestroy will be called at most once each time your app is run, these handlers are likely to be called many times while the app is running. Now this is where things get a little different. On almost all platforms, app lifecycles are deterministic. Generally, you'll start a program and it'll keep running until it either completes or the user cancels it. If you look at traditional desktop development, that means your app keeps running until your user chooses quit or exit from the file menu. At that point, you can save state and free resources. But as we know, on Android, lifecycles work a little differently. So let's take a closer look at exactly how that works now. So now go ahead and add logging statements to the onPause, onResume, onStop, onStart, and onCreate and onDestroy lifecycle handlers for the main activity. Start the app and try rotating your phone. Now observe the logs. What's the sequence of these lifecycle events that your activity goes through simply by changing its orientation? Starting with teardown, the app will first be paused, stopped, destroyed, and then recreated, restarted, and resumed. Let's see if we can figure out what happens when our app is terminated in the background. Start the app again, then hit the home key. Now launch some other apps before returning to ours. Try and pick apps with large memory footprints. Can you figure out which of the following lifecycle event handlers is the last one guaranteed to be called before your app may be terminated by the runtime? Since Honeycomb, Android apps can rely on stop being called before the app is at risk of being terminated. But if you're supporting pre-Honeycomb devices, you should prepare for termination as early as after onPause. Let's take a closer look at how you should prepare for an untimely app death. As you are moving around between apps, you probably noticed that from a user perspective, Android doesn't announce changes in app state. It doesn't announce that it's low in memory or ask users to close apps to free up resources. In fact, it does everything it can to make the resource limitations of the device invisible to the user. And that means keeping the foreground app running smoothly and switching between apps seamless. And that means killing apps in the background. And it does that if it needs their resources to make sure that the foreground apps can continue to run. So we know that as soon as your app isn't visible, its lifetime is as perilous as that of a Stark at the Red Wedding, likely to die without notice, but ready to return from the dead. That tells us some very important things about how our apps should behave to be good citizens and provide a great user experience. From a system perspective, onPause and onStop are signals that our app may be killed imminently. So we need to clean up any resources that need an orderly teardown, such as closing any open connections or sockets. For the purposes of the Sunshine app, this information is purely theoretical. In fact, you'll really only need to consider this later when you're adding things like sensor or location listeners. Until then, the default components will handle much of this behavior for you. In any case, now that you understand the lifecycle and the way that the system handles exiting your app when it needs its resources, you should hopefully understand why exit or quit buttons in Android apps serve no practical purpose. At most, you can call finish on an activity and it will get torn down instantly. But that's actually exactly what happens when a user simply hits back from within their activity. If you're still not convinced, check out the video in the instructor notes where I explain my reasoning with a little more color. As app developers, it's our job to maintain the illusion that once started, every app is waiting patiently in the background, looking for its chance to be the star when called on. So whenever the user switches back to your app, whether or not the system has killed it in the interim, they should be presented with the same UI they had when they left. To help, Android has a pair of handlers specifically for persisting state in these circumstances. OnSave instance state is called immediately before onPause, so as soon as your app is no longer active. And onRestore instance state is called immediately after onCreate, but only if the app is being restarted after having been terminated by the system. That means you can read the bundle of state information saved the last time your app was moved from the foreground here. The next time your user switches to your app, even if it was killed by the system in the meantime. Using that bundle, you can return your UI to the same state it was the last time the user saw it, creating a seamless transition that hides the resource management happening under the covers. But that's enough of the why. Let's go back to Dan and see how to put this theory into practice.
You may be thinking, Life cycles are really important. However, this section is on persisting and recovering data. Trust me, I just want to get us coding again. However, these things are closely linked, and they're easy to get wrong if you don't understand both. As Reto mentioned, Android saves the state of the application in bundles. You might have had the idea that you could just save all sorts of information in these bundles and not have to worry about any other form of persistence. But the thing is, these bundles go away as soon as the user hits the back key in your main activity. It's really important that they do this. When the user chooses to close your activity with the back key, the expectation is that the next time your activity is displayed, it will be in the default state. If the user backgrounds your app using the home key or the app switcher, the next time your activity is created, it should resume from the current state. Another thing that I wanted to mention before we dive into the code is that it's important to be a good Android citizen. This means adhering to the principle of minimizing network activity and having an app that works seamlessly between offline and online states. We're going to make that happen by creating a cached data model that is shared between the various activities of Sunshine. We've got to store our model somewhere. Fortunately, Android contains SQLite, a powerful database. It also has some great helper classes to make using databases straightforward. We're not going to be teaching database theory here, but we are going to do some pretty sophisticated things in practice. Let's start by defining a database contract between our data and our model. A contract is an agreement between our data model and our views describing how information is stored. It will contain all the fields that our user interface will display. This is a good time to revisit our final detail wireframe. For each weather forecast, we're going to need to store at least the date, the condition, the high and low temperature, the humidity, the wind speed and direction, and the barometric pressure. Since our databases will use a row to represent each forecast day, we'll store each piece of data associated with the forecast in a separate column. Let's go into Android Studio to begin coding. We'll add a new package to our project named Data to encapsulate the data model. Next, we'll create a contract class to store our column information. The inner classes within our contract class will be used to define tables. Each table will implement base columns, because the columns represented by base columns are useful. The ID column, in particular, must be a part of our table in order for our content provider integration to work later on in this lesson. Our database will contain weather forecast entries. Our data model will use two tables. One table will be used to contain information about the location, while the other will contain the forecast data key to the locations. These will ultimately be tied back to our view through the contract and the content provider. We can use an inner join to pull the complete data for each forecast day, including all information about the location. This is a big contract. Note that we store the location ID, which will be a foreign key from the location table in column loc key. Also note that the units aren't stored in the database. We expect all weather entries to be stored in metric units and converted when needed by the UI into imperial units. We need to create a contract for our other table that contains location entries. Location entries must contain a city name. This inner class will be created in much the same way as weather entry. It will implement base columns, contain the table name, and contain the names of each column. Note, the ID of each row in the location entry class will be stored in weather entry. All right, you're done. Let's take a look at the solution. And here's our solution. We begin with our unique table name. The rest of the inner class lists the columns we're going to use to store our data, postal code, and location name. Now that's a contract. But we still don't have a database. Our database class will extend an Android class, SQLite Open Helper. SQLite Open Helper contains cool stuff to help us handle database versioning. As we make changes to our database in the future, it will help us modify our tables. For many apps, being able to upgrade to a new version without data loss is critical. Let's create a WeatherDB helper class within the data package and have it extend SQLite OpenHelper. We can add the required methods by hitting Control-I, and we can override the constructor by hitting Control-O. So now we can hard code these variables to the constructor, hard coding name to database name, our factory to null, and our version to database version. Now you'll note I have made the database name public, and that's because we're going to use it in our tests in the future. Now you see we've got an onCreate and an onUpgrade method. In the onCreate method, we're going to start by creating a string to build the weather entry table using data defined within the weather entry contract. Now I'm just going to add this comment so you know where to go back and add the location entry stuff later. Since weather entry depends on location entry, I would normally write location entry first, but weather entry is pretty complicated, so I'd rather explain what we've done and leave location entry up to you. We're going to use raw SQL for our create table query, beginning with the table name from our contract. At this point, it's helpful to import weather contract.location entry and weather entry. It makes our query so much easier to read. We'll start with our ID field, which we'll set as our primary key and an auto-increment field. Note that integer is actually assigned value up to 8 bytes long in SQLite. Using the auto-increment feature doesn't do precisely what one might think. Setting up the ID as an integer primary key actually makes the value unique whenever you do an insert, but it may not always increment. It may reuse existing ID values if the records have been deleted. What auto-increment is really useful for is if you are synchronizing data two ways with the server. But we'll take advantage of it here because it makes data from our queries sort a bit more naturally because we insert them in the right order coming from the server. In general, we're using constraints on fields, in this case not null. We do this because it allows the database to do much of our parameter validation for us. The tricky part about doing it this way is that we don't get useful errors when these constraints fail, so it can be challenging to debug. We're using a human-readable string for the date. There's no strong reason for or against this choice. We wanted to normalize the date to simplify our queries, and human readability simplifies debugging. The date comes from OpenWeather in Unix timestamp format with some time information that we need to get rid of. I'm not going to cover every field. Real means floating point in SQL. It would have been fine to have used integer with fixed point math as well, and some would argue that this would be faster, but real is more straightforward since we're storing floating point values. Now for the fun stuff. We're going to set up the loc key as a foreign key to the location entry table that you will be building. This causes SQLite to enforce the relationship between the tables. We cannot insert a weather entry when there is no corresponding location entry. And we cannot delete a location entry if there are still weather entries that depend on it. Cool stuff, right? One last constraint. Our date text plus location must be unique. On conflict, replace the data. This allows us to insert new data from the OpenWeather API easily, preserving existing keys and updating the values if the forecast changes. Create a matching location entry table creating query from the location entry contract, using the weather entry one as a model. The good news is that this is a simpler query, and if you really hate databases, just move to the solution. A much simpler table. Just a standard primary key, a few values, and a few constraints. Note that we use onConflictIgnore. This means an insert into the database with the same key will not actually update the database at all, and therefore will also not return an ID in the Android helper functions. Well, now we're getting somewhere. All we have to do is run those table creation queries by calling exec_SQL at the end of our onCreate function. But wait! There's another function in our SQLite OpenHelper, onUpgrade. You might think, why should I care about those? I'm not upgrading anything yet. To make our development lives easier, we're going to implement the most standard kind of onUpgrade there is. You see, onUpgrade only fires if you change the version of your database. Remember, we passed that version into the SQLite OpenHelper base constructor ages ago. Since we are going to be using our database as a cache for web data and not for user-generated content, we'll drop the tables.
This is helpful if we want to change the database in the future. If we were using user data, we'd do something like use alter table to add new columns. So now we have a database. But it will be a while before we can test this in our code. We still are going to implement a whole layer on top of it, along with a bunch of UI changes. Fortunately, we can implement JUnit tests here to help. And now for some magic. We'll add a directory to the source directory of our Android Studio project called Android Test, and then another one underneath it called Java. This is the way we tell Android Studio there's a test target in Gradle for our app. Now we create a test package that matches our main package with an extra test directory on the end. Create a new class called Full Test Suite in the test package. Add this code. This is some boilerplate code that will allow us to add tests in additional classes. Next, we'll create a TestDB class that extends Android test case, and add a test that creates our DB. The way this works is that the test runner will execute every function in our class that begins with test in the order that they are declared in the class. Each test should have a failure path that uses an assert. We start by deleting the database before testing it, so we have a clean test. Now, to run the tests, we go to the App Start dropdown and select Edit Configurations. We select Plus to add a new configuration and select Android Tests against Module App. Now we name the test. Now note that it tends to target the emulator by default. Since I want to use an actual device, I'm going to select Show Chooser dialog. Now we can just run the tests against our device. And it passes. So let's create a database insert and read test. At the beginning of it, we'll insert a single record into each table. We'll begin with some dummy data for our location. We'll use the DB helper to get a writable database. This is exactly how we will use the database when we code it up in our project. We'll then create a content values object, which is a handy helper object that Android uses to store values and keys. We'll store our dummy data into the columns from our location entry contract. Note that in order to make it work with this abbreviated syntax, I did have to add some extra imports up here. We then insert the data into our database and verify that we got a row back. Now I find that it's helpful to put log messages into my test cases. Now we'll use the database read operations to pull our dummy data back out of the database. We're making use of a custom projection here, which in theory would make it easy to use our database cursor to query for the values we want. We use a custom projection here, although it's not required. If the custom projection wasn't there, we would simply return all columns. A database cursor is a control structure that enables traversal over the records in a database. In Android, this is represented by a cursor object. The cursor object allows one to traverse between records in a query and get the contents of any individual column from a query. Now we use cursor.moveToFirst to populate our cursor with our row of data. We can then pull out our data by index. Finally, assert if it doesn't match our dummy data. And now we get to run our tests again. And they passed. All right, as the comment says below, now that we have a location, let's add some weather. Let's implement the weather part of our insert read DB test. I'm going to give you some dummy data to help you out. Note that the location key is the row ID of the data we just inserted. Also note that I can use this short syntax for weather entry because I added this import at the top of the file. Alright, so we insert that provided data that I gave you into our database and verify that we can read it back out again. Alright, you're done. I hope you don't mind that I gave you the larger table this time, but it depends on the first one, so it would have been hard to give you it in any other order. I gave you the content value structure, so it's pretty easy to just insert the data. Then we query the data back out. If move to first fails, the cursor is empty and the query failed. Lots of cut and paste here. It is nice to fetch the DB values using the helper for the data type, although it's not strictly necessary since we know our test data is actually going to match our constraints. And there is one more failure case we need to add here, if our query doesn't return any rows. And that's it. All that just to get a database and a way to test it. Now let's run the test again. Well, at least we know all the basic stuff works. And just remember, without these tests, you wouldn't have been able to run this code for a very, very long time. All right, now for a little bit of an open-ended exercise. How could we simplify our test code? Write up a solution. A hint here is that we can take advantage of the read property of the content value structure. Here's how I ended up simplifying things. I'd love to see great testing ideas, so if you're particular to what you've created, post your solution to the forums. I'm starting off refactoring things a little bit. What I'm going to do is I'm going to add a function to get the location content values. This will be useful when we actually try to use these tests for some other things later on. And there we are, a function that will return location content values. I'm also going to pull the city name out so we can use that for some validation steps later on. And there we are. It's now inside of the function. And then we're just simply going to call that function to get our location content values, and we can delete all of those lines of code. Now, all of these columns, as I said before, are not very important, so we can delete them. And we can also null out the value in our query. The next thing I want to do is actually fix this validation step. What we can do is we can create a function that relies on the fact that we can get the map and set from our content values. Then we can simply iterate through those. Then we can see if the values that we use to create the record actually pass the values in the cursor that are returned. Now, back to our test. So there's a lot of unnecessary code here now. All we have to do is call validate cursor with our values and our cursor. All right, so now we've converted the first test. We can do the same thing with the second test as well. First of all, let's do the same abstraction we did before. Now, of course, one of these values isn't going to be static, so we have to add that in. So now we can say content values equals get weather content values with our all-important location row ID. Remember, our tables are linked. And then we can insert it into the database. Query for it. If the query is successful, we can just call validate cursor again on our weather values with our weather cursor. So much less code. And that's it. Our test is vastly simplified. And it will be useful to us later on. So now we can try running this test again to see if it still works after the refactoring. And there we are, our test passed. Now it'd probably be useful for us to actually print out some more data so we could see what was being tested. But this simplification to our test is going to help us as we move forward. We're not done with testing yet.